Today we wish to sketch the graph of a function that has terms with fractional powers. Uh, Sometimes students find such problems rather challenging. So our specific function is defined to be f of x is 2x to the 1/3 plus x to the 2/3. So our first step is going to be to find the derivative of f. So f prime of x is 2 times x to the 1/3, which is 2/3, x to the power 1/3 minus 1, or minus 2/3, plus the derivative of x to the 2/3, which would be 2/3, x to the power 2/3 minus 1, or negative 1/3. So let's rewrite our formula for f prime without the negative exponents. So we could write this as 2 divided by 3x to the positive 2/3 plus 2 divided by 3x to the 1/3 power. Okay, and next we'd like to write f prime as a single fractional expression. So to do that, we'll need the common denominator of 3x to the 2/3 power. So the second term needs to get multiplied by x to the 1/3 divided by x to the 1/3. So now we could rewrite our formula as 2 plus 2x to the 1/3 over the common 3x to the power 2/3. Okay, and maybe just one last step. Let's say, well, we could factor out a 2 in the numerator and write f prime of x in the form 2 times 1 plus x to the 1/3, all divided by 3x to the power 2/3. Okay, so this is our more compact form for f prime of x. So let's put that in a box. And we're interested in knowing where the first derivative is equal to 0. Okay, so f prime of x clearly will be 0 if and only if the numerator is 0. So that requires 1 plus x to the 1/3 power to be 0, which would mean that x to the 1/3 would have to be minus 1. Okay, and to solve for x, what we'll do is cube both sides. And so that tells us that x must be minus 1 cubed, which is negative 1. Okay, so this is the only point where f prime will equal to 0. We also notice, however, that f prime of x is going to be undefined when its denominator is 0, right? So that means x to the 2/3 would have to be 0, or in other words, x itself would be 0. So these two numbers we call the critical numbers for the function. They're the numbers where the first derivative is either 0 or undefined. Okay, so next we're going to compute the second derivative function. Okay, so now to compute f double prime of x, and for that it's going to be easiest if we go back to our original formula for f prime and differentiate that form, which would just involve differentiating a sum rather than differentiating this form in the box, which would involve use of the quotient rule. So going back to our first form for f prime, we differentiate that. So we'll use 2/3 times the derivative of the power, x to the minus 2/3. So 2/3 times minus 2/3 would be a minus 4/9. X to the power minus 2/3 minus 1, or minus 5/3. Okay, and then plus 2/3 times the derivative of x to the minus 1/3. So 2/3 times minus 1/3 would be minus 2/9 x to the power minus 1/3 minus 1, or minus 4/3. So this would be our formula then for the second derivative. So as in the first case, we could rewrite this expression for f double prime without using negative exponents if we write minus 4 over 9x to the power positive 5/3 minus 2 divided by 9 times x to the power 4/3. So just like in our form for f prime, we said we'd like to rewrite it as a single fractional expression. And so again, we'll need a common denominator, which in this case is going to be 9x to the 5/3. So this second ratio needs to be multiplied by x to the 1/3 divided by x to the 1/3. And so now we could rewrite our formula as minus 4 minus 2x to the 1/3 all divided by 9x to the power 5/3. And again, you know, in the numerator, there's a common factor of minus 2. So if we pull out the minus 2, we could write minus 2 times, okay, 2 plus x to the 1/3, all divided by 9x to the 5/3. Okay, so here's our factored, here's our fully factored form for f double prime. Okay, and so so let's put that formula also in the box. And we also need to examine, right, where is our second derivative going to equal to 0? And that, of course, would be true if and only if the numerator is 0. So that means that 2 plus x to the 1/3 would have to equal to 0, or x to the 1/3, in other words, is minus 2. And again, if we cube both sides of that equation, we find that x itself is equal to minus 8. Okay, so minus 8 makes the second derivative equal to 0. And notice that the second derivative would be undefined, right, whenever the denominator is 0. So x to the 5/3 will be 0 only when x equals to 0. So just like the first derivative was undefined at x equals 0, so of course the second derivative is undefined at 0. So now what we're going to do is we're going to take these points that we highlighted, namely 0, minus 8, and minus 1, and use them to split the x-axis into several subintervals. So let's just say we'll draw our x-axis up here, and we'll indicate, say this is going to be the location of minus 8, and then say here's negative 1, and say here's 0. And so what we saw was that at minus 8 and 0, okay, so let's put those two numbers in boxes. Right? Those were the numbers where our second derivative was either 0 or undefined. Okay, so they're splitting the line up into 3 subintervals. But then we also had an additional point, namely at minus 1, which is a point where the first derivative was 0. So let's put that number, say, in a circle. And we also found that at 0, the first derivative was undefined. Okay, so those numbers were numbers significant for the first derivative. So where our function could change from increasing to decreasing at those two numbers, possibly. And so let's in fact examine, the sign of f prime of x over the real line. So in any case that our x is less than minus 1, then the cube root of x to the 1/3, is also less than minus 1. So that's going to make our numerator negative. Now notice that the denominator, x to the 2/3 power times 3, that can never be negative, right? Because after we take the cube root of x here, we're going to square it, right? So as long as x is not 0, the denominator is positive. Okay, and consequently, we have when x is less than minus 1, always a ratio of a negative to a positive, which is negative. So the first derivative is always negative when x is less than minus 1, right? That means, right, that the graph of f is decreasing since the graph has negative slope over that interval. So f is decreasing here, still decreasing over here. Notice, however, though, when x exceeds minus 1, then the cube root of x is greater than minus 1. And as a consequence, this numerator will be positive when x is greater than minus 1. Again, the denominator is positive, for all such x except 0. And so we'll always get the product of something positive divided by something positive, both between minus 1 and 0, and for x greater than 0. And so we always have positive slope to the graph of f. Positive first derivative means the function of f is always increasing on the interval from minus 1 to infinity. Now let's also examine, the sign of the second derivative function. Okay, so now let's consider the sign of the second derivative, which is given by this factored form. Okay, now when we select any value of x that's less than minus 8, then the cube root of x is also less than minus 2. So that's going to make this factor in the numerator negative. Okay, so we get a negative times a negative. So the total numerator is positive, but any negative number to the 5/3 power will be negative. So therefore we have, when x is less than minus 8, a positive divided by a negative. So the quotient is negative. So that means that our function f is concave down on the interval minus infinity to minus 8. It's also decreasing. So its graph would have to have this sort of shape to it. Okay, so as it decreases at faster and faster rate over that interval. Okay, now between minus 8 and 0, if we take the cube root of any such number in that interval, that will now be greater than minus 2. So this factor 2 plus the cube root of x will now become positive. And so we get a positive times a negative, which is negative on top. The denominator, right, again, any negative number to the 5/3 power is negative. So if you have a negative divided by a negative, the quotient is positive. So we have positive second derivative whenever x is between minus 8 and 0. So that means our graph of f is concave up. And so between minus 8 and 0, f will be decreasing but curving up. So now as it decreases at a slower and slower rate. However, between minus 1 and 0, it's going to increase and be curving up. So the graph on the interval minus 1 to 0 would be shaped like that. So it's increasing at a faster and faster rate as it increases between minus 1 and 0. And then finally, when x is positive, Then, of course, 2 plus the cube root of x is positive. Okay, x of 5/3 is positive. So this quotient is going to be always negative. So our function f, therefore, will be concave down on the interval 0, infinity, and it's increasing on that interval. So the shape of the graph is like that. So it increases at a slower and slower rate as it rises to the right of 0. So we kind of connect all of these arcs together to get the full, complete graph of the function. So let's just summarize what this table tells us. So it tells us, as we said, that f is decreasing on the interval from minus infinity to minus 1, inclusive, and f is increasing on the interval from minus 1 to positive infinity, inclusive. Okay, and then we also saw that f was concave down, in fact, on 2 intervals. So f is concave down on the interval from minus infinity to minus 8, and also on the interval from 0 to infinity. F is concave up in between. F is concave up on the open interval from minus 8 up to 0. Okay, and now let's figure out specifically the points on the graph that correspond to the extreme points and the inflection points. So if we go from left to right here, at minus 8, the value of the function would be, we go back to our original formula for f, plug in minus 8 for x, we get 2 times the cube root of minus 8, that's minus 2. The cube root of minus 8 squared minus 2 squared is 4. So the value of f at minus 8 is 0. So that means, minus 8, 0 is an x-intercept for the graph. And we also see that at that point, the concavity changes. So that tells us that the point minus 8, 0 is in fact an inflection point for the graph of f. So our next point has an x-coordinate of minus 1. The value of f at minus 1 is going to be 2 times the cube root of minus 1, which is minus 1. The cube root of minus 1 squared is plus 1. So minus 2 plus 1 is minus 1. So we see that, the function was always decreasing to the left of minus 1, increasing to the right at minus 1. So that means the point minus 1 is a relative minimum point, and in fact it's also the absolute minimum point. So this is both a relative minimum point and also the absolute minimum point. So also, let's say, and the absolute minimum point on the graph of f. Okay, and then our next and final point of interest is when x is 0, f of 0 is clearly equal to 0. And so, so what happens at the origin is that we have this change in concavity. So we know that at the point 0, 0, the origin, it is a inflection point. And also notice that, remember how, the first derivative was undefined when x is 0. And in fact, because as x approaches 0, the derivative becomes unbounded in the positive sense, the graph must have a vertical tangent line at the origin. Okay, so in addition to being an inflection point, it is also a point of vertical tangency. And why is that, right? Since when we take the limit as x approaches 0 of the first derivative function, the numerator, you can see, clearly converges to 2 times 1, or 2, divided by 3 times something that's going to 0. But notice that it's always going to 0 through positive numbers, since we're raising x to the power 2/3. And so 2 divided by something that's nearly 0 but positive, right, that ratio just becomes bigger and bigger, and it's unbounded, therefore, in the positive sense. So we have an infinite slope to the graph at the origin. Okay, so now, let's take all of this information and see if we can use it to help graph the function f. Okay, so we see again, with respect to x, our points of interest lie between -8 and 0. So let's just try to draw in here a horizontal line to represent our x-axis. Okay, so if we say this is going to be our point -8, and let's say here's going to be the origin, and let's say we move over here, about would be x equals 1. If we went another unit to the right, let's say that would be our location for 2, and to the left of 0, we'd have say here's -1, let's say, is there, and so therefore -2 would be around that location on our number line for x. Okay, and we see the values for y of interest are 0, -1, and 0. So the points stay fairly close to the x-axis. And so what we'll do is use a slightly different scale along our y-axis. So let's say here comes the y-axis. Say, hey, this is going to be 1, like 2, 3 on y, and so here it'd be like, say, -1 on y. Okay, and I'm going up to 3 here. Okay, so this is our y. And so again, we're going to plot our points. We had the point at the origin, right, was our inflection point, and our point of vertical tangency. So indicate, like here's our tangent line. It's like vertical here at the origin. We had another point of inflection was this other x-intercept -8, 0. We had the minimum point on the graph was -1, -1. Okay, and maybe just to get a point on the graph to the right of the origin, it's pretty clear that if we let x equal to 1, that f of x is 2 plus 1 equals to 3. Okay, so this just happens to be another point on the graph of the function. And of course at the minimum point, -1, -1, the slope was 0. The graph has a horizontal tangent line. And perhaps it would be valuable to determine the slope of the graph at the inflection point -8, 0. So for that, the slope would be given by the derivative of f at -8. So let's just maybe fit it in here. F prime at -8 would be, by this formula, 2 times 1 plus the cube root of -8. So that would be -2. 1 minus 2 is -1. Divided by 3 times the cube root of -8 squared. -2 squared is 4. So that's minus 2 over 12, or minus 1/6. So this is the slope at the inflection point, minus 8,0. Okay, so let's draw in the tangent line to the graph at that point. Okay, so that means that, if we move minus 1 unit in the y direction, we would move 6 units to the right in the x direction. So in other words, the tangent line at minus 8,0 will pass through this point, minus 2, minus 1. So let's try to draw that in our graph here, and we would have this sort of a tangent line. Okay, and so good. So now what we know is that the graph of f, it's decreasing always and concave down from minus infinity to minus 8. So therefore the graph is always below this tangent line at minus 8 when x is to the left of minus 8. So the graph looks something like this, decreasing, concave down. Then between minus 8 and minus 1, the graph continues to decrease, but it's concave up. So the graph lies above this tangent line here, right, between minus 8 and minus 1, and it bottoms out here, at minus 1, minus 1. So the graph is, nearly linear, but slightly, curving upwards, okay, as x, as the graph decreases from minus 8,0 to minus 1, minus 1. Then between x equals minus 1 and x equals 0, the graph increases and it turns to be concave up, and it has this vertical tangent line at the origin. To the right of 0, the graph continues to increase, but now it's concave down, okay? And we know that it passes through this point 1, 3. So the graph of f would have to have roughly this shape. And so again, this is just the this tangent line at minus 8,0 was a line of slope f prime at minus 8, which is minus 1/6. And so that's a fairly careful and detailed drawing of this graph of the function y equals f of x. So I hope you found this example helpful in solving homework problems on graph sketching. So thanks for watching. Goodbye.